to the next talk. I'm extremely happy to introduce my close colleague and friend Pascale Senellart from CNRS and CDZN Lab in the University of Paris-Saclay in France. Hello, Pascale. So Pascale will be talking to us about progress and challenges in quantum dot single photon sources. Thanks, Pascale.
Thank you, Eleni, for the introduction. Thank you very much. I would like to thank the organizers for coming up with this beautiful meeting that allows the quantum community to catch up despite this weird moment. So I work at the Center for Nanoscience and Nanotechnology. It's a CNRS University Paris-Saclay joint unit near Paris. And in my group, we develop semiconductor devices based on quantum dots to both generate and manipulate quantum light. So you can see here some images of these devices. And today I will present some recent progress we made on single photon source and one application, mostly. So I don't really need, after this first two beautiful talks of this session, to motivate quantum light, why we need quantum light for quantum technologies. I mean, quantum light is needed everywhere, different flavors of quantum light. But we need them for quantum cryptography if we want to go to high rate or long distances, for quantum computing and even remote quantum computing. And of course, for different kinds of quantum networks based on different schemes, based on memory or measurement, etc. So in this talk, I will go to discrete variable. And if I think of all these applications in this framework, the ideal light source that we need is a light source that produces light pulses, that each pulse contains just one photon. And of course, this is a very idealistic picture. And in practice, we will always have losses, which means that we have vacuum sometimes. And so a matrix of this technology is the brightness of the source, which is basically the probability to have one photon per pulse. For many applications, we want to have pure quantum state, indistinguishable photons, because we want the photon to undergo some kind of interaction, which is actually based on the quantum interference, the Hongo-Mandel interference, where two photons impinging on the beam splitter exit the beam splitter together. So I will present very briefly in the first few minutes of my talk our quantum light technologies that we've developed over the last decade, basically, and what are the ingredients that have made the devices work better and better over time. So our system is an indium-gallium arsenide quantum dot gallium arsenide. So these are artificial atoms that have been known to emit single photon in the last 20 years now. To efficiently collect the single photon, we put this artificial atom in a cavity where you have two Bragg mirrors, one top, one bottom, and a lambda cavity here. And this cavity implements cavity quantum electrodynamics, which basically means that we accelerate the spontaneous emission of our atom into a given cavity mode. We accelerate by the Purcell factor here, which means that the probability for our quantum dot to emit in the mode is given by this beta coefficient here. It's not enough. Of course, we also need to make sure that the photon emitted into the cavity mode exits the cavity through the right output. So here in our micropillars through the top. And this is what we call the output coupling efficiency. And with these two ingredients, back in 2013, we managed to have a single photon source with a brightness, so probability to have one photon per pulse of 80%. That was important for us, but it was not enough because we needed the photon to be in a pure quantum state, to be indistinguishable, which means that we needed to fight any coupling of the quantum dot to an uncontrolled environment. So in semiconductor devices, one of the sources of decoherence is charge noise. So we reduce charge noise by using the full semiconductor possibility of including the quantum dot in a diode structure. So to do that, we slightly modified our devices. This is still the dot, the cavity, but instead of etching all around, we keep Wendy ridges so that we can implement an electrical contact further away from the dot. And with that, we could reduce very significantly the charge noise.
Pascale, can I please interrupt you for 1 second?
Yes.
We cannot see your slides advancing. Do you mind sharing your full screen, please, so that we can see your slides?
Wow, what's going on then? I've been sharing my full screen from like 5 minutes since I started.
So let's see.
What can I do then? So you have not seen anything I've shown so far?
We're on the first slide still.
Oh, okay. So I am on slide 10 now. So do you see my screen like this if I don't share my full screen?
We can see your screen now, but you need to advance the slides by hand.
This?
Yes, like this. Yeah.
This
this
is what I
one.
was doing, but in the full screen mode. So I'm very sorry for that. So just what you missed is this slide, very basic, about quantum networks and quantum applications. The matrix of a single photon source, the devices, a quantum dot in the micropillar cavity, and I was going to the electrical control of the devices here. Okay, so we'll continue like this.
Okay, thanks,
And
Pascal.
do you see my mouse? If I move,
can you move it? Yes, we can see your mouse.
So I'm not going to go full screen. I'm gonna keep it like this. Okay.
Okay, whatever works best.
I think I was full screen before. It didn't work, so I won't go back then. Okay, so I was on the idea that to produce indistinguishable photons, we need to reduce charge noise. So we included the quantum dot in a diode structure like this. That was one of the first ingredients that we developed. The other one is to use a unitary excitation scheme. We need somehow to control the full trajectory of our qubit before it emits a single photon. So for that, we implemented coherent control and following many works in the community doing that, but doing that also in the cavity. And then we worked on reducing the phonon decoherence. So of course, like for any solid state emitter, there is a possibility for the emitter to couple to phonon and to have this phonon silence. And we could show a few years ago that using cavity QED again, you can strongly reduce the probability for the quantum dot to couple to the acoustic environment and strongly reduce this incoherent part of the emission spectrum. So doing that, what we could show as a community is this a great increase of the efficiency of single photon source. So this is the map that we published in 2016. You can see here the indistinguishability of the photon and here the brightness of the source, the ideal source being in the upper right corner. On the bottom side of the graph, you can see SPDC, so single photon source based on heralding and frequency conversion, which are bound to very low efficiency, around at best 1%. And you could see that the quantum dot community as a whole has increased the efficiency of the sources by more than an order of magnitude, with a brightness in the 10 to 30%, with an indistinguishability well above 90%. If you think in terms of qubit, which means that you are basically gaining a factor at least 10 per qubit, so you have an exponential gain in terms of qubit production. And the best illustration of how this kind of technology can speed up optical quantum technology was provided by our host, Xiaoyang Lu and Zhanwei Pan, that demonstrated last year a 20-photon boson sampling experiment for the very first time. So I want to now head into the next scheme for us. As developers of this kind of devices, we are now working harder to increase the brightness and go toward the deterministic source, the source that produces 1 photon each pulse. And I want with this scheme to underline how challenging this is. This is a cryostat where we have our quantum dot source. This is the first objective. So we want first a quantum dot photons to be emitted into this first lens objective. And then we need to optimize all the setups that we need to operate the source and couple the photons into a fiber so that we can send it on a quantum processor of different types. So this is the second step, is just maximizing the setup efficiency. But the first step is more tricky, and it's much more about solid state physics and quantum optics. We need to optimize the probability of emission into the mode, engineer the cavity so that the photon escapes through the top. We need to find schemes where the quantum dot occupancy is as close to 1 as possible. And of course, we also have a high degree of polarization. And we need to maximize all that at once to reach very high efficiencies. Until now, there was some limitation in the schemes that we were using to produce a single photon. Just without entering into too much details, but still for you to understand, we needed to operate the qubit with resonant excitation, which means that the single photon we're collecting are at the same frequency as the lasers that we use to pump the qubit. So to separate the quantum dot photon from the laser, we basically use a cross polarization scheme. We pump in one polarization and collect in the other polarization. And to do that, we mostly use charged quantum dots because they present a 4 energy level structure where you have, for instance, a hole in the quantum dot. You have 2 possible states for the holes. And the optical selection rules link this hole spin state to an excited state with either right circular polarized light or left circular polarized light. This kind of optical selection rule is at the heart of spin-photon entanglement schemes. We can, of course, rewrite this optical selection rule in a linear basis, which shows you that when we pump in H, we pump the two spin states, and we can collect photon in the cross-polarization H here under this diagonal transition. But of course, it means that the polarization degree of such source is below 50%, which limits eventually the efficiency of the source to 50%. So it's not a good scheme for going to a deterministic source. So recently, in the group of China-Lu, they proposed the first way to get rid of this problem is to use a polarized Purcell effect. They make an asymmetric cavity that has polarized mode, and by doing that, you can favor a Purcell factor that is stronger for the H polarizations here, for instance, like it's shown here, than for the V polarized scheme here. And by doing that, they managed to go beyond the 30% brightness, which was the upper limit before that, to a first lens brightness of 60%, which is beautiful. The same scheme was also recently implemented by the group of Richard Warburton in Basel in Switzerland, this time with a different kind of cavity, an open cavity system, and they even pushed the number further by having a fibered brightness of 57%, which means that they also optimize very much the setup collecting the photon. So here I want to present another path that we are proposing to go towards a deterministic source. And what I like about it is that it's actually based on our better understanding of the solid state physics of the systems. We are back to solid state physics to push further the technology. And the first thing that we do is exploit the natural asymmetry of the quantum dot. Quantum dots, because of the semiconductor structure and because of the intrinsic shape of the quantum dot, they have reduced symmetry, the C2V symmetry, which means that if we take a neutral quantum dot, a quantum dot where there is absolutely no charge without prior to excitation, the level structures is a three-level structure. You have one ground that connects to two excited states, which are X and Y, linearly polarized states, which are split with this, what we call the fine structure splitting. And this state is actually a naturally polarized single photon source. Of course, it's more difficult to explore such kind of states because you cannot use resonant excitation. So the other ingredient that we use is to use a phonon-assisted excitation. We stop exciting resonantly like we did for the last few years, and we slightly detune the laser on the blue side. And when we do that, we use phonons to populate efficiently the excitant state. But doing that, we can now excite and collect in every polarization as we want. So we can excite X and collect X or collect Y. And this is what you see here. We excite X, collect X or Y, and you see that we have a highly polarized single photon emission with a polarization degree above 99%. You can see that this kind of polarization degree is ideal to have a deterministic source, and actually it can reach one. There is no fundamental limit to the degree of polarization you can reach with this scheme. Of course, I have introduced another ingredient, and I need to show you that it's not detrimental to the source. So the idea is to use phonons. So we start with a two-level system for the quantum dot. If I go into the rotated frame, and considering that my laser is detuned, I have now this excited and ground state, which are split by the laser detuning. And then we switch on the laser and we dress the states. And we dress the states, and these states are dressed by the laser, are now very nicely spaced in energy so that it's very convenient for them to go from one state to another through phonon emission. So all this scheme is based on some theoretical papers that were published in the last few years. And you can see the dynamic of the system. When I switch on the laser, we start in the quantum dot ground state. During the pulse, there are the dressed states here, phonon emission, that brings my system at the end of the pulse with a very high probability into the excited state. So these schemes are very nice because they show actually here that the excitant population that is calculated as a function of the pulse area, if you are resonant, you have this nice Rabi oscillation that we have been exploiting so far. If you're using this phonon-assisted scheme, you can see this red line here that goes to a population of almost 1, although the laser is detuned from the quantum dot. Most recently, just last year here, it was shown that you can combine this very high occupation probability with a very high indistinguishability, which actually shows that the scheme that we are presenting here is very close to unitary transformation. So we studied this prediction experimentally, and we could show that the occupation of the state can indeed be very close here to the one you can get under resonant excitation. We managed to observe an 85 occupation probability for the quantum dot state. Then we could check that the quality of the single photon is not affected by the fact that we are using photon-assisted excitation. This is what we see here. This is a single photon purity, G2, and a Hongu-Mundell experiment, where you can see that on the left, it's resonant excitation. On the right is photon-assisted excitation. We have very similar value of 91 and 92% indistinguishability in both cases. And these numbers here are limited by a slight residual phonon sideband. So you can see here below that actually we can have even higher numbers, adding slightly a small filter to the scheme. So we can indeed produce very high quality single photons. And now we can see that we can reach much higher performances. So this is now the brightness of the source as a function of the pulse duration and the detuning of our laser. And you see that we can reach here values that are as high as 53% first lens brightness with a scheme which provides a near unity polarization degrees of the single photons. Very high indistinguishability, single photon purity, and all these numbers show you that now the next challenge for us is actually to optimize our cavity structure, keeping the other values close to 1 as they are here. So this is another path toward the deterministic source. And what we like about it is that it's very easy to implement. It makes a huge difference in the lab. And if you think of application, if you want to give the source to other researchers to exploit them, this is very important. Especially, it's very robust to any kind of twist. As you can see, the single photon rate is hardly dependent on the detuning of the laser and the pulse area of the laser. And this makes a huge difference if, again, you want to make practical devices. The last feature that we like very much about this scheme is that it allows us to collect single photons in any polarization and excite in any polarization. And this is exactly what we need to generate linear cluster states using the Terry-Rudolph scheme, for instance. And this is what we are now exploring in this European project. So I will now go to an application of our single photon source. We are not there yet to generate linear cluster state with spin, but we have worked with Agai Eisenberg from the University of Jerusalem to generate linear cluster state in a sequential way. So you will see, I will go into the detail of this scheme. I don't need too much to motivate why we want to generate cluster state of light after the last talks. Just as a quick reminder, it's a very interesting scheme to move toward the scalable quantum computing with optics. Because, of course, we all know that linear optics is probabilistic. It does not scale very well. So there are these theoretical proposals since 2003 to use cluster state and measurements to scale up quantum computing. And this practical discussion by Terry Rudolph a few years ago, where at least we need 3 photon cluster states to move forward. There was a lot of demonstration on how to generate this cluster state, all based on the parametric down conversion sources, piling up several kinds of sourcings, leading up to 12 photons in the group of Chailong Lu 2 years ago. These schemes requires a lot of resources, and we are more interested in the long terms in this scheme proposed by Terry Rudolph and Lindler back in 2009, where you use a spin to successively untangle a photon, several photons. So the idea would be like we use the spin of a quantum dot, we excite the quantum dot, and each photon is emitted by the spin. So we can do that sequentially together with the manipulation of the spin and generate linear cluster state. So we are working on that, but we are not there yet. What we are doing is something which I think is a bit intermediate with Agai and very elegant, which is the idea that we take our sources, we generate photons sequentially in time, and we use a delay loop and a gate to untangle successively photons in a probabilistic way, but in a very compact and with a nice scaling ratio way. So just to show you, all these measurements were done in collaboration with a group of Agai, and they came with their setup in their suitcase here, where you have everything, the untangling rack and the electronics. And we did the measurement combining our 2 technologies. And actually, at some point, they could even run the experiment from Israel, having our source in Paris. So the scheme is the following. We are a quantum dot in our devices. We generate trains of photons, And we then send the photon into this first entangling beam splitter, and you have here the delay loop, which is a gate, which is acting as a memory. And all this fits into this very compact box here. And at the output here, you have a linear cluster state. And in the same box, you have also what you need to analyze the state. And here you have electrical polarization controllers all along to do the analysis of the state. We can describe the scheme with this corresponding logic circuit, here illustrated for 4 photons. So it's meant for 4 photons entering the system. So for each photon, they will undergo a succession of operations, Hadamard, Z and Hadamard gate, phased Hadamard gate, etc. And here at some point, the first photon will meet the second one, etc., etc. And you see on top the physical implementation corresponding to each box, either a standard polarization controller or a beam splitter or a loop or detectors and a beam splitter for the analysis at the end. So to show the non-local interference, we actually perform a phase gate on the qubit inside the loop on the n-1 qubit inside the loop. And we record the events as a function of this phase. And you can see here the result for 2 photons, 3 photon, and 4 photon cluster states. And the visibilities of the 2 photon interference are expressed here. And you see data obtained for different single photon sources on our side with different indistinguishability and count rate. So from this kind of measurements, the group of Agai has find a way, although we cannot perform with these schemes a full tomography of the state, they were able to extract a bounded entanglement witness, an entanglement witness which is the lower bound of a number that, if it's below 0, it shows entanglement. Oh, there is a problem here with the, sorry, some errors in the subscript here. It's just the values of this entanglement witness that we've shown. This entanglement witness is well below 0 for all the states that we measured, generated up to 4 photons. So what we also like about this scheme very much with Agai is to consider how much we can scale up the schemes to go to larger number of photons. So we introduce this matrix, which is the scaling ratio. It's actually how much your detection rate reduces, the reduction factor, when you add 1 photon to the scheme. Because we all know in optics is that the problem is that the count rate decreases drastically when we go from n to n+1 photons. So here the scaling ratio is shown as a function of the quality of the 2 photon indistinguishability, the 2 photon interference. We are still using a probabilistic gate here, so the upper limit is 1/2. The ideal situation would, of course, be here a scaling ratio of 1. The blue curve here is the intrinsic limit with heralded single photon sources, which have an inherent compromise between the efficiency and the quality of the interference. The blue symbols are the best sources that have been reported so far, especially in the group of Zhang Ruipan and Xiaolong in China. The red spots are the previous work. And dark and light symbols are with limited detectors that we have right now in the lab, and the one that we could get just having more efficient detectors based on superconducting nanowire detectors. And you see that this scaling ratio already now with our quantum dot sources allows to already scale up much better than what we could do with heralded single photon sources, and we can work a lot to improve all that with the latest development I've shown you. So I'm almost done. I wanted just to mention 2 other recent works that I cannot go into the detail, but it could be of interest for specialists. We have a deterministic technology in my lab. We fabricate devices with the full control of the quantum dot position and cavity position, etc. So we've been able to do some benchmarking of our technology, and we could show, we could study the reproducibility of different sources, so 15 sources, showing all of them very high indistinguishability, similar lifetime. And we are currently working on the possibility of having indistinguishable photons from remote sources. And another paper that will soon appear in PRL, where we have revisited a little bit the Hongo-Mendel interference with imperfect sources trying to model the effect of the extra photon on the two-photon interference, showing two very striking features that if the extra photon is identical or not from the main one, you expect, of course, a very different impact of the Hango model interference. And it is very important to be able to extract properly the single photon indistinguishability that we want to optimize in all these devices. And with that, I want to thank you for your attention. This is the team that did all the beautiful work that I've shown you, and all this has been possible thanks to very nice samples grown by Aristide Lemaitre, technology help with Isabelle Sain, close collaboration with the team of Quandela, that is a spin-off company commercializing the single photon sources. And of course, beautiful work also with Agai Eisenberg, as I mentioned, and theory support from the group of Alexia Ofev. Thank you for your attention.
Thank you very much, Pascale, for this nice talk. We could follow everything perfectly after the small correction. So let's go. We have a little bit of time for a couple of questions. We have one question from the audience, Chao Yang Lu. What is your estimation of the maximal count rate of indistinguishable single photons when pumped by 80 megahertz repetition rate laser the community can reach in 5 years? What are the remaining challenges, in your opinion, Pascale?
Okay, so I think, the remaining challenges, as I mentioned, I think right now, we are, in our technology, I think in the micropillar technology, we are still limited by losses on the pillar. So basically, I think we have, with the LA phonon, we can go even further to the occupation probability. Polarization degree can be one. So what's remaining, and we are working on it right now, are the losses in the cavity. So doping losses and geometry losses. And so we are now conducting studies that we couldn't conduct in the last few years because our clean room was shut for 2 years, so we couldn't do any improvement on that side. And we are trying to be very systematic about it. I think we can reach output coupling efficiency of, I would say, within 5 years. I think 90% is within reach. So then 90%.
Actually,
yeah.
Go ahead, Pascale. Sorry. Go ahead.
Is within reach, 90%. Then on the indistinguishability side, right now we are suffering a lot on basic classical optic ingredients, because even though we can cut a lot of phonon Simon, we still have a few percent that we want to get rid of. And so then I think in practice, 80% single photon efficient, highly indistinguishable photon in the fiber within 5 years is very much reachable. Yeah, I think that's a reasonable goal for the next 5 years. Reasonable, I think, yeah.
And Zhao Yang is also asking, what are the most promising structure? Pillar, bullseye, open cavity, or photonic crystal?
Yeah, so I think Shayon knows as well as I do what the answer to that is complicated. I think bull eyes are great for untangled photons, but I think I think high Q cavities are very important to get rid of phonon Simons, and we cannot really hope to have highly indistinguishable photon without that, because the filter doesn't do the same job as cavity QED here. We have all been very impressed by the result of Richard Warburton using an upper cavity, and I think this is very nice. But having worked now 4 years within the spin-off company to try to make the source available to other researchers, I think the monolithic device is still the best path, because you don't want to have too much constraints on vibration, etc. We want really a robust device that can go in a vibrating cryostat, the same cryostat that the community is already using for superconducting nanowire detectors. So I think my vision on that is that we need a high Q cavity to have the highest indistinguishability. We want to shorten as much as possible the time the dot interacts with the environment. And we need the most integrated structure that we can think of, so that we can really put it out of the lab and make it like a plug-and-play machine.
Very nice. Okay, we're out of time, but I still have a very, very short question. I liked very much the work with Hagai on the linear cluster state. And I wanted to ask you, how much is it possible to extend those ideas, these practical, basic ideas, to other cluster states? Like, more complicated ones?
Sure. So just first, we were stuck with 4 photons because of the very poor detectors I had. So I think right now we can just use the same source, have 8 photons or 6 or 8 photons very soon. So that's still 1D. Of course, the idea to go 2D cluster state is to have an active element in the loop. Right now, everything is passive. So we just set the thing once for all, and that's it. And so we have just this passive way of generating one cluster state. The next move for us is to put an active element, replace the beam splitter with an active element, and then we can go to a 2D cluster state. So this is basically on our roadmap for the next few years.
Very nice. Okay. Thank you very much, Pascale, for your wonderful talk and for the answers to the questions. No problem at all. Thank you, Pascale. Bye-bye.